Okay, so today I won't be here. Today there's a track meet. Tomorrow, though, yes, for tomorrow, I will definitely make the request. I'll put a sheet up, okay, for tomorrow. All right, so this quick review of the stuff we talked about yesterday. If we're trying to just find an inverse of a function, let's just quickly go through what are the steps we go through to find an inverse. So what are we going to do? Mallory, what do we do if I start off, I'm given this as f of x, and I want to find the inverse? What do I do? First step. Okay, write it in terms of y. So I'll turn the f of x into a y. And I'm going to include the domain, right? That's important. Okay, what's next? What's next, Nick? What do I do next? Flip the y and x. Good. Okay, so we switch y and x. So I'm going to put, this becomes a y, that becomes an x. I'm going to put the y part on the left side of the equation. So 3y squared minus 3 equals x. And what's it do to, this was the domain, right, of my original function, because it's defining the x values for this relationship, for this function. Switch the x to a y. Good, so that's going to become, what do we call that? If it's a set of y values, it's not the domain, it's the range. Good. So that becomes the range of our inverse. Because what's the last step going to be? Maria, what do I do last?
You add.
Okay, so go ahead.
The last step, you do the exponent.
Right, okay, and you're looking at specifics. I understand what you're saying, and you're correct. But just in general, the next step is I switched x and y, and now what do I do?
You divide by 3.
Well, I'm gonna solve for the new y, right? So you're giving me specifics, which is great. You're giving me the specific steps. I just want to know in general. Once I switch the x and y, I'm going to go solve for the new y, right? Okay, now, what are the specifics? To get that y by itself, what do I do first? I add 3. How come?
Inverse operation.
Okay, good. So, real quick, I want everybody facing the front. Hannah, I want you facing the front, please. If you want to sit there, you got to be facing the front. So, I've got to work backwards through order of operations. If you ever are at all unclear about what do you do to get something by itself in this situation or any, if I'm ever solving for a variable, which is the same thing as isolating a variable, remember, it's super easy. All you do is we reverse order of operations, right? So we're just going to go bottom up. So, okay, so correct. So first thing is add, subtract. Yes, we're going to add 3 to both sides. Okay, good. That gives us 3y squared equals x plus 3. What's next? Multiply, divide. What do I have to multiply or divide here? Divide by 3. And when I divide by 3, I'm dividing the whole side by 3, aren't I? Right? Okay, good. And so then we end up with y squared equals, good, we're going to square root. If I want to, whenever I have a common denominator, I can split that into both fractions. So I could write that, for example, as x over 3 plus 3 over 3, which is what? 1. And then last step would be square root. I want to undo the exponent by square rooting. And so I would get y equals what? Plus or minus, that's important. We got to put the plus or minus the square root of x over 3 plus 1. How do we know we need the plus or minus there? Why'd you say that, Joe? You're right. Okay, because I'm taking an even root, right? Because that's an even power of y. I'm having to take an even root of both sides. That always means plus or minus. Okay, but remember now, there's one other part that I hopefully haven't forgotten about. We've got this y is greater than or equal to 0, right? So if I've got a square root function here, the output of a square root function is always going to be what? Okay, but let's not even focus about the plus or minus part. If I were just to put numbers into a square root, what's the square root of 100? Positive 10. What's the square root of 9? Positive 3. What's the square root of negative 100? Oh, red flag. Problems, right? If we're looking for real solutions, then we couldn't even do that, right? But if I'm taking a square root, I'm either gonna get a positive answer, or at the lowest, right, the smallest value I could get out would be square root of 0, which is 0. So I could get 0 or positive outputs, but not negative, right? So if the answer, if y has to end up being greater than or equal to 0, how does that help me here? I'm only gonna take the positive ones. I'm not gonna take the negative ones, right? So I'll eliminate the negative sign. So my answer would just be then, the inverse function is just positive square root of x over 3 plus 1. Now, how would things change? What if this problem were different? What if it said instead, let's just say hypothetically that it said the domain of the original function is all values of x less than or equal to 0. Yeah, then I would have only taken, that would have meant eventually that we would have gotten down here, y is less than or equal to 0, so we would have just taken the negative, right? Make sense? Okay, good. Okay, what about a problem like this? What would the steps be here? So same as before, right? If I'm finding an inverse, first I write it in terms of y, switch the x and the y. Let's put the y's on this side, so we get 9/4 y cubed plus 2 equals x. What are the steps in order to get y by itself? First I'm going to, well, subtract 2. So I'm going to get an x minus 2 gets rid of that. Now what? How do I undo multiplying by 9/4? Yeah, multiply by the reciprocal, right? We don't really divide by fractions, we just multiply by the reciprocal. So I'd multiply both sides by 4/9 to get rid of that. Okay, what did I do wrong over here though? What did I not do that's important? Parentheses. Because I'm not just multiplying the x by 4/9, I'm multiplying both sides of the equation by 4/9, right? So that means everything. Make sense? So that would get me down to here. And then the last step, cube root. Do I need a plus or minus? No, how come? Ever?
Because there's no domain, or like, it doesn't have the x is greater than or equal.
Okay, so, I see what you're saying. Even if I hadn't been given this right here, I still, when I take a square root of both sides of an equation to find solutions, I still need that plus or minus, right? That's just because this is an even power. Okay, but you're correct. I don't need a plus or minus. How come? Because it's an odd power, exactly. So I'm taking an odd root of both sides. So taking a 3rd root or a 5th root or a 99th root, no matter what it is, if it's an odd root, I don't need a plus or minus. So my answer is just going to be y equals the cube root of that. Okay? No problems. Now I don't have to worry about the plus or minus stuff. Make sense? Okay. Quick review. We're going to go back and think about some stuff that we did earlier in the year. So what if let's look at the graphs of some really simple power functions, just simple cubic functions and simple quadratic functions. If I want to take something like, let's take a parent function, let's take the parent function f of x equals x squared, and we're going to tweak that a little bit, right? What does the parent function look like? What is the graph of x squared? Oh, I'm seeing this, good. It looks like that, doesn't it? So it's going to be, it's going to look like a U. And in order to kind of make this more specific, give me some points it goes through. Where's the vertex going to be? At the origin, okay, 0, 0. What other points does it go through? If I go over 1, how high do I go? 1 squared is 1. Okay, so if I go backwards, negative 1 squared is 1. So it's just going to look like that, right? Everybody agree? Okay, so it starts at the origin, goes through the point at 1, 1, and negative 1, 1, right? So now, what could I do if I wanted to slide this thing horizontally? What would I do? How could I do that? How could I take the, I want to write a new function, let's call it g of x. Yeah, go ahead. So if I want to tweak this, I'm going to do some transformation. So I've got g of x. What's some stuff I can do to x squared to stretch it, compress it, slide it, do all that kind of stuff? What can I do? You remember what those? Let's do this differently. What are the parameters that control that? H and K, good. And what else? That's good. H and K. What else we got? So what about the H and K part? So that's going to be, I'm going to get x minus h. Whoops. Right? So instead of just an x, if I subtract h from x, what does the h control? Do you remember? Horizontal shift. Yeah, h for horizontal. Let's get how far we're sliding or translating horizontally. What about vertically? What did I do? What was the parameter associated with a vertical slide or translation? K. Yeah, so we could just add k to that, and k is our vertical shift, right? Good. And then A, good. If we put an A out front, very good. That's compression or stretch vertically, right? And that's usually all we need, that stuff, right? We could also add a 1 over B in there. We're not going to mess with that for now, at least, right? So that's all the stuff we typically need to do to a function to tweak it, right? So, okay, good. Good. So if I wanted to, you tell me then, what if I graph this function instead? Let's say I've got one that's going to start, it's going to start up here at the point 2, 3, and it's going to go over 1 and up 2. So that's going to be the point 3, 5. That's a pretty crappy parabola, but you get the idea. So what's that one going to be? What are the values of A and H and K that I could plug in and tweak my parent function with? What's H? Bailey, what's H? How far do we slide this thing horizontally to get it up there? Well, H is just the horizontal, how far we slide it. It starts at 0, 0. Where did it end up? It ended up, the vertex is instead at 2, 3, right? So how far do we slide it horizontally to get it there? 2. Yeah, 2. And so you see right away that H is just the x coordinate of the vertex, right? Okay, what's K? I think there's the vertex. What are H and K? Those are just the coordinates of the vertex, because that's how far we slide it. So K is 3, right? And then now the other part's a little trickier. What's A going to be? Normally, if we go 1 to the right from the vertex, we should go up by 1. How far did we go up this time? We went over 1. We went from 2 over to x equals 3. But then the y value went up by how much? By 2, right? So if we do that, if we go over 1 and up 2, what did we do then? Did we stretch it or compress it vertically? What did we do? Yes. We stretched it by how much? 2, right? The point got pulled up twice as far as it normally would be. And so this would tell us that A is equal to 2. So what would our function be? Well, our function then would just be, if we wrote that, it would just be g of x equals, I'm going to plug in 2 for A times x minus, well, h is 2, plus 3, right? That's it. Everybody see that? Okay, no big deal. How could I take this function and flip it upside down? What's gonna be negative? A is gonna be, right? A is positive if it opens up, and it's negative if it opens down, right? So that's a vertical reflection. Everybody see that? So if this thing had done like this instead, same places, then we would have just had to have a -2 out front. Okay, agree? Okay, all right. What about a cube function? So that's a quadratic function. All the same stuff applies. We don't really have to do a ton of stuff here. We can just start with a different parent function. What would the parent function look like for a cube function, a cubic function? Yeah, good, that's that one, isn't it, right? Okay. So that's the one that's gonna do this. It's still gonna go through the same points, right? It's gonna go through the point 1, 1, 0, 0, only this time it's gonna go down on the other side, so it's -1, -1, right? But we can do the same stuff to it. We can drag it around, we can stretch it, compress it, do all that stuff, right? Same stuff applies, the same kinds of transformations. All right, so why do we bring this up? Here's why we bring it up, because what if we want to do a problem like this? This is one that we kind of started talking about yesterday, but we reviewed our thinking on some of this stuff, we kind of reviewed what it means to be an inverse function, but now let's put this into a really efficient process for solving a problem like this. And what are they asking for? They're giving us a function and they want us to do 3 things. They want us to, A, write what the inverse function is. You just did a bunch of that. That's no problem. Piece of cake. Step 2, we want to write the domain of the inverse function, and step 3 is write the domain of the original function. Okay, so let's think about this now. What kind of a function is this? It's going to be quadratic, right? It's going to be a simple quadratic. So its parent function was the one we just looked at. That's just a simple parabola. Yes, sir. Oh, okay. All right. And Everett. All right. I'll see you guys up there in a little bit. We're getting warmed up. Bring home the gold. Come on.
Let's get this name.
Will you?
No.
Okay, so what did we do to this? We took the parent function, and what did we accomplish here? Brooke, what did we do by adding 2? Moved it 2 in which direction? Up. Good. So we just took the function and moved it up by 2 is all we did, right? So then if we were to graph this, it's just going to look like a normal parabola that's been shifted up by 2. So the coordinates of the vertex are 0, 2. Everybody agree? Okay. So now what about the inverse? Let's think about this. What would the inverse be? The graph of the inverse is going to be reflected over what line? The diagonal line. Not the x-axis. It's going to be the line y equals x, right? So here's the line y equals x. So that's the line of reflection, right? So where is this point going to go? Remember, the inverse, the graph of the inverse, we're just switching x and y. So the vertex of the inverse is going to be, instead of at 0, 2, is going to be where? No, 2, 0. I'm just going to flip the x and the y, aren't I? Right? So we're just going to go over 2, and there it is. And then what's this parabola going to do? Well, this parabola is going to go like that, isn't it? Right? Everybody agree? Okay, there was a problem with that we looked at yesterday. What's wrong with the inverse graph? It fails the vertical line test, right? Fails the vertical line test. How could we have predicted that based on the original graph? Fails the horizontal line test. Good. So a function that fails the horizontal line test is guaranteed to have an inverse that fails the vertical line test. And that's the big problem, isn't it? We talked about this using different vocabulary at the start of the year. Let's just put it in that context, because this is sort of a big deal. So we talked about relations as being 1 to 1, many to 1, and 1 to many. And then we could have many to many too, but we're not gonna mess with that one, right? So what does that mean? Well, all that means is input values compared to output values. So let's go back and look for just a second at our quadratic function over here. So we got a point at 0, 2. We could also say up here, if we go over 1 and up 1, we're gonna have a point at 2, 3. But then I should also have a point over there with coordinates what? If I go backwards 1, what's the x value? Oh, sorry, that should have been 1, 3. Oops, that probably confused you. Right? Everybody see how I got that? If we go from the vertex, which is at 0, 2, if I go over 1, I should go up 1, right? So my x value goes from 0 to 1, my y value goes from 2 to 3, okay? So what about this one over here? It's gonna be at negative 1.
One.
Same y value, isn't it? Negative 1, 3. Everybody see that? Okay, so then if we were to make a table out of that, if we made a table of values, like we did earlier in the year, so look what we got here. I've got a value when x equals negative 1, that maps to y equals 3. When x equals positive 1, that also maps to 3. What do you suppose that is then? Which of those classifications fits that relation? No. Many to 1. Yeah, it's a many to 1, isn't it? Because I've got many x values mapping to 1 y value. So many inputs to 1 output, right? Make sense? It is a function, but its inverse was a problem. If we look at the inverse, what are the corresponding points going to be down here? Well, instead of being at 1, 3, what's this one going to be at? 3, 1, right? We flip the x and the y. So those points will go together. That's at 3, 1. This guy right here is at, maps to what? 3, negative 1. Well, what's that? If I make a table for that one, let's see, the value x equals 3 maps to 1, and it also maps to negative 1. What's that going to be? 1 to many, and that doesn't work. 1 to many is not a function. Because think what a function means. For every input, there's exactly 1 output. Well, that didn't happen here. I had 1 input and 2 outputs, right? So there's the problem, right? So what I have to do is I've got to somehow, if I want to have an inverse of my original function, I've got to erase part of my original function, right? I've got to restrict the domain so that it passes the horizontal line test, right? So instead of being a many to 1 function, we're going to turn this into a 1 to 1 function. Because really what a 1 to 1 function means is a function that passes both tests at the same time, vertical and horizontal, right? So what could we do then? If we go back to our original function, how could I keep as much as possible but erase everything I need to make it pass both tests? What's a good strategy, do you think? Where's going to be the point where I would maybe start erasing? The vertex, right? Good, I could start at the vertex, and how about if I just keep everything in quadrant 1, right? Because that's the most convenient place, right? So let's just go back and erase all of this stuff, right? So we'll get rid of all that, we'll just keep this part. Well, that has an impact on the inverse then too, doesn't it? Right? If I erase the left half of the original parabola, then I'm also erasing the bottom half of its inverse. And now everything's great. Now I have a 1 to 1 function because I got rid of this, didn't I? Right? I got rid of that, and so I get 1 input, 1 output, which means I also got rid of this guy. So it also becomes 1 to 1. See what I'm saying? Okay? So then, all we have to do here, if I want to answer the first couple questions, really, I don't even have to graph the inverse. I could do this same exact problem without even bothering to graph the inverse, because all I really need to know is what's going to be the domain and range of my original function. I'll show you what I mean. So let's take this same problem and let's do it a little bit differently. Okay, so we know right away that the vertex of this function is where? I don't even have to really graph it. Where's the vertex? What's the value of h? H. No. 0, right? And k is 2, right? Because there's no number being subtracted from x inside the square. Everybody agree? So that means h is 0. And the number that's being added at the end is 2, so that's k. Agreed? So then we know that we only want to keep the values, Joe's strategy was a good one, we're only going to keep the values that are greater than or equal to the x value of the vertex, right? For our, I'll just throw the picture up real quickly, not that we even really need it. Our picture just looked like this. We're only going to keep those values, right? This is the part that, it's there, but we erased it. Agreed? Okay, so if the coordinates of the vertex were 0, 2, then what are those x values? What's going to be the domain of the original function that we're going to keep to make it 1 to 1? X is what? Well, okay, or what else? It's an infinite number of points, but 0 is important. X is greater than or equal to 0. In general, we could just say it's going to be greater than or equal to h, but h is 0, right? So we end up with, that's our domain, right? What's the range going to be? A set of y values. A is positive, so it opens up. So 2 is going to be the cutoff value this time, isn't it? The lowest value is going to be the value of the vertex, and we'll keep everything above that for the range. Everybody see that? Okay. So the range is just going to be all values greater than or equal to the y value of the vertex, right? Because it opens up. If it opened down, we'd have to go below it, right? Okay, well, what about the inverse? So this is all the stuff for f of x. What about for the inverse? What's the domain of the inverse going to be compared to the range? Don't even have to think about it. What's the domain going to be? What's the meaning of an inverse? What do you do to get an inverse? Switch x and y. So we're just switching the domain and the range, aren't we? Right? So what's going to be the domain of my inverse function? Say it again. No. 2. It's going to be all values greater than or equal to 2, right? Because, see, there's the relationship. What used to be my range now becomes my domain, right? What's the range of the inverse? Okay, and we could see that. If we graphed it, that's what we're going to see, right? We don't have to graph it, but it's going to look like that. So yeah, the domain is all values greater than or equal to 2, and the range would be all values greater than or equal to y equals 0, right? So I don't even have to do any of the graphs. I got everything just right from knowing where the vertex is. What's the domain of the original in interval notation? Well, it's going to be everything greater, all x values to the right of the vertex, including the vertex. So there it is, right? What's the domain of the inverse? Whatever the range of this is, right? It opens up and the y value is 2. So it's going to be that. Now if they want inequality notation, that's fine. We would just say x is greater than or equal to 2. Right? You get it? See how that works? Okay? And first part's easy. Then finally we could go back and solve for, we could switch x and y and solve for y. Okay, what about, what about that? Super easy. Super easy. I don't really have to hardly do anything here because what's my parent function going to be? X cubed, and I've just tweaked it by moving it up 5, right? But what can you tell me about x cubed? If I graph that, this is the one, that's this one, right? So it's going How is that one classified? So 1 to 1, 1 to many, many to 1. It's 1 to, yeah, it's 1 to 1. How come? Yeah, it passes both tests, horizontal and vertical, right? So that means it's inverse, guaranteed to be 1 to 1. So do I have to erase the domain at all? No, we're good. So written as an inequality, what's the domain of the inverse, guaranteed? X is what? No restrictions. How would I say that with inequalities? Yeah. X is greater than negative infinity and less than positive infinity. What about the domain of f of x written in interval notation? What's that going to look like? Negative infinity, comma infinity, right? Because it's a cube. It's a cube function. Cubes and cube roots are fine. They're 1 to 1. They don't fail any of the tests. You're good. And then we could do this one easily, right? You've had a lot of practice at that. Okay, no big deal. All right, so there's a fringe benefit of this, something that comes along that's really handy, right? So we've done problems like this before. This is actually a problem that I could have given you many, many moons ago. This could have been when we were doing Module 3, right? If we go back to Module 3, which was solving quadratic equations, this was the easiest kind. We kind of focused on the harder kinds, but this was really simple. What would we have done to solve this? What do we always probably do first? But we got to kind of clean things up, right? So what would we do first? Eli, what would we do first here? If we're going to solve this equation, and I want to kind of get things cleaned up and simplified first, what would I do? Do you see any like terms up there? What do you think? See any like terms? The 6 and the 42, good. What about those? Are those like terms? Yeah, the x squareds are, aren't they? So we could combine like terms just to kind of clean things up. So that'll make things look a lot simpler. So let's do that. So if I were to, for example, subtract 18x squared from both sides, what am I going to get on the left side? How many x squareds? 100. 118 minus 18. So I get 100x squared, and if I add 6 to both sides, what's negative 42 plus 6? Negative 36. There you go. Okay, good. Right? Now we could solve this as a difference of squares, but we didn't even know about that earlier in the year, and we still solved this in an easier way, actually. What did we do? Yeah, we said, remember, we've always said at that point we were talking about solving quadratics. If we could point to a single x, we didn't have to do anything like factor or complete the square or quadratic formula. We just isolate x, right? So what are the steps to get that x by itself? First we add 36, then we divide by 100, and then we square root, keeping in mind the plus or minus, right? That's it. Pretty simple, right? So if we do that, then we end up with x squared equals 36 over 100, right? If I square root both sides, x equals plus or minus the square root of 36 over 100. But I could always split that into separate square roots. So the square root of 36 over the square root of 100, what's that? 6 over 10, right? So I get plus or minus 6 over 10, which is plus or minus 3/5. Okay, those are my two answers. Easy, right? Isolate x. Okay, here's the good thing though. You can do this for equations that aren't quadratic. You can, right? It's going to work for other situations too. There's one thing you got to be careful about though. For quadratic equations, it's going to give you all of the solutions, imaginary, all the complex solutions, right? If we had a problem, if we go back to that last page, what if we had something instead, real quick, what if we got down to a point where we got something like x squared, instead of equaling 36 100, say we just had x squared equals negative 4. What are we going to get if I square root both sides? What's the square root of negative 4 going to be? The square root of 4 gives me 2, and the square root of negative 1 makes it an I. So we even got back the imaginary solutions in this case, right? So it works for all situations for quadratic equations, right? But problem like this, now we would normally have, I'm going to tweak this just a little bit so this is a little bit easier. Let's make this instead 2x cubed plus 16 equals 0. Okay. How would I do this one? The way we've been doing this. So if we're doing this the way we've been doing this, like as of yesterday, right? Wouldn't we just divide both sides by 2 and get x cubed plus 8 equals 0? And so yesterday we would have said, what does that look like? What pattern does that look like? It looks like a sum of cubes, doesn't it? Right? Doesn't that look like x cubed plus what cubed is 8? 2. And then we could just factor that. And what's that going to give us? What's that pattern tell us? Sum of cubes. X cubed plus 2 cubed factors into what? What's that going to be? What do we think here? Emma, what's that going to be? So you remember that pattern? Sum of cubes. X plus 2. Now what? We got x cubed plus 2 cubed. So I get a plus b times what? Remember? Somebody help her out. What do we? X times a squared, which is x squared, minus ab, 2x, right? Plus 2 squared, so plus 4. Right, remember that? Okay, real quick, Mrs. Bidorf showed me something kind of cool with this. If you want to keep track of the signs, here's just a simple way to keep it kind of remembered. So first sign is same, second sign is opposite, last sign is always positive, so it's soft, right? That's how you do the signs. Okay, but anyway, we'll keep going with this. So this is all equal to 0, right? So if I set these equal to 0, I'm going to get x equals -2, right? What about this one? If I set this one equal to 0, I could use the quadratic formula, and I'm just going to get x equals -b would be 2, right? Plus or minus the square root of b squared, -2 squared is 4, minus 4 times 1 times 4 is 16, right? Everybody see that?
Yeah.
All divided by 2 times 1. So that's going to become 2 plus or minus the square root of -12. So the square root of -12, what does the square root of 12 simplify to? What's the biggest perfect square factor of that? Square root of 12 I can break into the square root of 4 times 3, square root of 3, right? So we get plus or minus, square root of 4 is 2 times the square root of 3, but it was a negative, so I'm also going to get an I there. If you're not following all these steps, don't worry about it. I want to make a point with this though. Divided by 2. And so we end up with, if I split that apart, I could divide both by 2 and get 1 plus or minus the square root of 3i. It's a lot of work. I got my 3 solutions though, didn't I? But what if the question only asked for the real ones? If the question only asked for the real ones, I wouldn't have had to even bother with this one, right? Okay, here's my new strategy, and this is all we're doing today. Then we're done. What if instead, when I was clear up here, I don't even need very much room for this. I could have just said instead, let's just isolate x, right? What would I do to isolate x? Subtract 8 from both sides? So I'd get x cubed equals -8, so x equals the cube root of -8, which is what? -2, right? Boy, that was pretty fast, wasn't it? That a lot easier?
Yeah,
That's
that was
it.
so great.
Right, if all I want is the real solution, if I don't need to find any eyes or anything, why would you might as well just isolate X, right?
All solutions, we have to do all that.
Yeah, if you want all solutions, you gotta factor it. If you want all complex solutions. Oh, that's a lot of stuff.